Hello, welcome back, guys. Today we will understand this paper. Okay. Also need to write it. Okay, let's start reading this paper, guys. So first paper is to how to read papers. Then we will go to the real paper, which is logical physical clocks. Okay. Let me edit this also. Right, like this, and this. Okay, so it's a bit more. Right. Alright, so here we were reading this first pass. Incidentally, when you write a paper, you can expect most reviewers and readers to make only one pass over it. So take care to choose coherent sections and subsections titles, and to write concise and comprehensive abstracts. If a reviewer cannot understand the gist of after one pass, the paper will likely be rejected. If a reader cannot understand high lines of the paper after 5 minutes, the paper will likely never be read. For these reasons, a graphical abstract that summarizes a paper with a single well-chosen figure is an excellent idea and can be increasingly found in scientific journals. Then the second pass should be our. In the second pass, read the paper with greater care, but ignore details such as proofs if help to jot down the key points or to make comments in the margin. Okay. As you read, Dominic Grossman from University of Oxford suggests that you note down terms you didn't understand, questions you may want to ask the author. If you are acting as a paper referee, these comments will help you when you are asking your review and to back up your review during the program committee meeting. Look carefully at figures, diagrams, and other illustrations in the paper. Pay special attention to graphs. Are the axes properly labeled? Are they also with error bars so that conclusions are statistically significant? Uh, Common mistakes like these will separate rust shoddy work from the truly excellent. Okay. Next thing is remember to mark relevant and read references for further reading. This is good way to learn more about background of papers. Okay. And second pass should take up to an hour for an expected for an experienced reader. After this pass, you should be able to grasp the content of the paper. You should be able to summarize the main thrust of the paper with supporting evidence to someone else. This level of detail is appropriate for a paper in which you are interested but does not lie in your research specialty. Okay. Sometimes you won't understand a paper even at the end of the second pass. This may be because the subject matter is then new to you with unfamiliar terminologies and acronyms, or the authors may use a proof or experimental technique that you don't understand, so that the bulk of the paper is incomprehensible. The paper may be poorly written with unsubstan- unsubstantiated assertions and numerous forward references, or it could just be that it's late at night and you are tired. Okay, so you can now choose to A, set the paper aside and hoping you don't need to understand the material to be successful in your career. B, return to the paper later, perhaps after reading background material. C, preserve and go on to the third pass. To fully understand the paper, particularly if you are a reviewer, requires a third pass. The key to the third pass is to attempt to virtually re-implement the paper. Okay, that is making the same assumptions as the authors. Recreate the work by comparing this recreation with the actual paper. You can easily identify not only paper innovations but also its hidden failings and assumptions. Okay, this pass requires great attention to detail. You should identify challenge every assumption and every statement. Right. Moreover, you should think about how you yourself would present a particular idea. This comparison of the actual with the virtual lends a sharp insight into the proof and presentation techniques in the paper, and you can very likely add this to your repertoire. What to say that? Repertoire repertoire of tools during this pass. Okay, of tools during this pass, you should also jot down ideas of for future work. This pass
He must have sung every song in his repertoire last night.
Repertoire. Repertoire, guys.
Repertoire.
Repertoire. Repertoire. Repertoire. Repertoire. Repertoire.
Repertoire.
Repertoire.
Repertoire. Repertoire.
Repertoire. Repertoire. Alright, and repertoire. Repertoire, guys. Okay, so yeah. During this pass, you should also jot down this pass can take many hours for beginners and more uh, than hour or two even for an experienced reader. At the end of this pass, you should be able to reconstruct the entire structure of the paper from memory, as well as be able to identify strong and weak points. In particular, you should be able to pinpoint implicit assumptions, missing citations to related work, and potential issues with experimental or analytical technique doing a literature work. Okay. Okay, then this shower can take many hours. At the end of this pass, you should be able to like that. Doing a literature survey. Paper reading skill are put to the test in doing a literature survey. Okay, this will require you to read tens of papers, perhaps an unfamiliar field. What papers should you read? Here is how you can use the three-pass approach to help. First, use an academic research engine, such as Google Scholar or Sightseer, and some well-known chosen keywords to find three. 5% highly cited papers in the area, and do one pass on each paper to get a sense of work, then read their related work sections. You will find a thumbnail summary of recent work, perhaps if you are lucky, a pointer to recent survey paper. If you can find such a survey, you are done. Read the survey, congratulations, you are on the good luck. Okay. Otherwise, in the second step, find shared citations and repeated author names in the bibliography. What is bibliography? Bibliography, right? What does it mean? Bibliography. A list of the books and articles that a writer used when they were writing a particular book or article. Okay. This is bibliography, guys. These are the key papers and researchers in that area. Download the key papers and set them aside. Then you go to website of the key researcher, whatever. Related work. If you are reading a paper to do a review, you should also read Timothy Roscoe's paper on writing reviews for system or whatever. That was a reference. That's it, guys. Now we will come to the real paper. Okay. This is our paper. It's 13 of pages. Right. We will do it. First, the abstract. We have to read the abstract first, right? So let's understand. It is written by, the name of the paper is Hybrid Logical Physical Clocks. Logical and physical clocks. Okay. Inconsistent snapshots in globally distributed databases. Sandeep Kulkarni, they Murat. What is this star? No. Murat Demerbas, Deepak Mandepa Leoni, Mandepa Bharadwaj Avva, Marcelo Leoni, Michigan State University, University of Berkeley. There is a gap between the theory and practice of distributed systems in terms of time. Okay, so the theory of distributed systems shunned by notion of time. What is shunned here? Let me search it. Shunned. Shun. You have to avoid somebody something, to keep away from somebody something. Okay. So distributed shunned the notion of time. Okay. And introduced causality tracking as a cleaning abstraction to reason about concurrency. Okay, so they shunned means avoid the time notion of time, but what they did, they introduced causality tracking, right, as a clean abstraction to reason about concurrency. Okay, the practical system employed physical time NTP information, but in a best effort manner due to the difficulty in achieving tight clock synchronization. What? The practical system employed physical time NTP, right? Information, but in a best effort manner due to the difficulty to achieve tight clock synchronization. In an effort to bridge this gap and reconcile the theory and practice of distributed systems on the topic of time, we propose a hybrid logical clock, okay, HLC, that combines best of logical clocks and physical clocks. Okay, Hybrid logical clocks HLC captures the causality relationship like logical clocks and enables easy identification of consistent snapshot in distributed systems. Okay. Dually, a hybrid logical clock can be used in lieu of what is this lieu? L I E U. L I E U. Lieu means instead, guys. Okay. So instead of physical NTP clocks, in lieu of, or we can say instead of, right? In lieu of physical NTP clocks, since it maintains its logical clock to be always close to NTP clock. Moreover, HLC fits in a 264 bits NTP timestamp format and is masking tolerant to NTP kinks and in masking tolerant to NTP kinks and uncertainties. Okay, we saw what is this kinks mean, guys. Kink, I think I have heard this term, but let me be sure with this, right? All right. Uh, Dually, HLC can be used in lieu of physical NTP clock since it maintains its logical clock to be always close to NTP clock. Moreover, HLC fits in 264 bits NTP timestamp is making rule. Okay, we saw that HLC has many benefits for wait-free transaction ordering and performing. So wait-free is a keyword here, right? What is wait-free here? Wait-free transaction ordering and performing Snapshots multi-version globally distributed databases. Okay. So it's just an introduction with a brief history of like logical clock, right? Then they are saying the physical time, what is that, right? Then hybrid time, they defined that. A true time, okay. Then they have hybrid time, the contribution of this work, okay, and preliminary, okay. Hybrid logical clocks, problem statement. Then it has description of the naive algorithm, HLC algorithm, okay, and Is the algorithm right? Then some theorems they have. Corollary theorem 4, properties of HLC. Okay. Then resilience, self-stabilization, masking of synchronized errors, experiments, AWS development result. Okay. So the experiment they have done some experiment. These are the numbers also. Okay. And okay, these are some experiment they have. And discussion snapshot. Okay, snapshots and compact timestamp using C, conclusion, other work. Good, it's a good paper. Right, we can read it. This is first pass, but we did it understand, but we will try to understand. Okay, everything it is same. Oh. Alright guys, let's start reading it, right, and understanding each aspect of this paper. So we already read the abstract. I think we know that. Let's go from the introduction now. Brief history of time. Albert Einstein said time is an illusion. Why he said that? Logical clock. Logical clock 12 was proposed in 1978 by Lamport as a way of time stamping and ordering events in a distributed system. Okay, so logical clock is discovered from physical time. For example, the NTP clocks. NTP is like, I think, network timestamp protocol. I don't know, network time protocol, like that. NTP is there. Okay. The nodes do not have access to clocks. Okay, so there is no bound of message delay and on the speed rate of processing of nodes. Okay, so let's understand from here, right? Okay, let's try understanding from this. Where is my help book? Can you explain this in simple language and in brief, right? Let's break it down in the simplest way possible. Why we need a logical clock? Okay, so we need a logical clock because in a single computer events happen one after another, right? So we can use the system clock time to know which event happened first. We can do that, but in a distributed system, many computers connected over a network. It's a distributed system. Each computer has its own clock. Their clocks are not perfectly synchronized. That's true. And so we cannot trust physical time to decide the order of events. So what do you mean by physical time here? Physical time is the time on computer. Okay, so Lamport introduced a logical clock in 1978 to solve this problem. So what is happened before? Lamport defined a relation called happened before. Okay, it means if event E definitely occurred before event F, then we write E happened before F. Okay, this does not mean earlier according to the wall clock. It means the system knows that E caused or preceded F. Rule 1. The system sentence you quoted, event E happened before event F, if E and F are on the same node. Okay. A node means a computer or a machine in the distributed system. That's correct. So event E happened before event F if E and F are on the same node. Okay. Example, computer A is there. E means E is event. Let's say read file is event. Okay. Then F send message. G save log. Since the event happen one after another on the same computer, E, F, G, we can write in this order. Okay. So everyone will agree on this order. Simple real life example. You open a question paper, event E, you start writing answers, event F. Obviously it's like that. Okay. This is the happen before relation. What logical clocks does, instead of recording real time like 10:15:1, 10:15:2 like this, it simply assigns increasing logical numbers like event E logical clock is 1, event F logical clock for this is 2, event G logical clock is 3. It means 1 is come before 2 and then 3. Okay, then these number tell us order of events, not the actual time. Okay. key idea, one sentence. Lamport logical clock does not measure time. It only tells us the correct order of events in a distributed system. It's very interesting, guys, right? LC logical clock is divorced from physical time. Okay, the node does not have access to clocks, and there is no bound on message delay or in the time step of processing nodes. The causality relationship captured called happened before is defined based on the passing of information rather than the passing of time. Very important. This is the same, but we will read it in more simple way. Okay, like this, and we have this, and whatever. What is this? Okay, whatever, but okay. Physical. And E2 corresponding. I don't know this, and can you explain this in simple English and in brief? Obviously, right? What happened here? Now, okay, let's explain each sentence in a very simple language, right? So, original sentence is LC is divorced from physical time. For example, the network NTP clocks. Simple meaning, logical clock has nothing to do with real time. Okay, it does not use your computer clock, wall clock, or NTP network time protocol, which synchronizes clocks over the internet. Okay. Instead, it only keeps track of order of events. Right. So original sentence: the nodes do not have access to clocks. Simple meaning. Right. Imagine that computer cannot see the current time. They cannot say event A happened at this time, event B happened at this time, right? So they need another way to decide which event comes first. So there is no bound on message delay, right? This sentence of this meaning of the sentence could be like when one computer sends a message to another, computer A sends a message to computer B. Nobody knows whether the message will arrive in 1 millisecond, 1 second, or 10 seconds. Okay, there is no guaranteed maximum delay. Okay, no bound on the speed rate of processing of nodes. Simple, different computers may not may run at different speeds. For example, A finishes a task in this second and when B finishes the same task in 50 milliseconds. Since computers work at different speeds, we cannot use processing time to determine event order. That's true. The original sentence here from the paper is the causality relationship happened before is defined based on passing of information rather than passing of time. That's very important, guys. It is based on passing of information, not the passing of time. Okay, so you understand this very important idea here. A causality relationship is defined based on passing of information rather than passing of time. Let me write it in bold also. The causality relationship is based on passing of information, right? Not on passing of time, right? Very important. What is this causality relationship? This is happened before. A happened before B, like this, right? Instead of asking which event happened earlier in time. Now we are not talking in time now. Lamport asked, did information from one event reach another event? If yes, then the first event happened before the second. That's the parameter here. Okay. So computer A. So there is a event E of sending message. That information is received by computer B, and that event is called event F. Now we can say event E sent some information and event F received that information. Now it means E happened before F, because information flowed from E to F, right? Not because of clock time. Okay, so Lamport logical clock ignores real time, instead orders event by tracking how information, or you can say message, flows between computers. Very important idea, guys, right? We return passing of information rather than passing of time. Okay, this one is like saying, okay. While being beneficial of the theory of distributed systems, logical clock is impractical for today's distributed systems. Okay. For one, using logical clock, it is not possible to query events in relation to physical time. Okay. B, for capturing HB, what is HB? Happened before. LC assumes that all communication occurs in a present system and there are no back channels. So this is obsolete for today's integrated, loosely coupled systems of events. Nice. So we will do that also here. Right? We will try to understand this. Can you explain this in simple language and in brief, right? We will understand that. It says like this paragraph is explaining us why Lamport logical clock is not enough for modern distributed systems, right? So first sentence in original paper is while being beneficial for the theory of distributed systems. Okay. The logical clock is impractical for the distributed. It's impractical for today's time. Simple. Lamport logical clock is great for understanding the theory of distributed systems. Okay, so लेकिन why it is great? Why? In brief and simple language. But today's system like cloud services, microservices like map or like payment system, these are microservices, right? Distributed databases, etc. are much more complex. So Logical clock alone is not practical. Problem 1 for that, using logical clock, it is not possible to query events in relation to physical time. That's correct, because it is not using physical time, right? The simple meaning, logical clocks only gives numbers like 5, 6, like that. It cannot answer like what happened at 10:30 or so, all events between 2 p.m. and like this, right? Because LC does not store real time, only the order of events. That's correct. Problem 2 for that is for capturing happened before, like passing of information, right? To capture the passing of information, LC assumes that all communication occur in the present system. Simple meaning, Lamport assumes that every message travel only through the distributed systems. For example, service A, service B. If A plus B, LC can track it. Okay. What are back channels? A back channel is another communication path outside the system. For example, service A can influence service B, it's normal. But Alice calls Bob on phone. Bob manually updates service B. So Alice is only influencing Bob, but or service A is emails, database, human shared files, something. The service B takes the information from email or like that, right? Here information travel outside the system. Lampological cannot see these hidden communications. I think I don't understand this well for now. We will understand, try to understand. Why this problem today? Modern applications are connected to many external systems, APIs, cloud services, databases, email, humans, message queues, third-party services. Information often flows through these back channels, so LC cannot capture this complete cause and effect relationship. So Lamport logical clock is good for ordering events, but it cannot tell the real world time and assumes all communication happens as a system, which is no longer true in modern systems. Also, I didn't just do this. Why the logical clock particular today? There are two reasons. It does not know real time. It's correct. I do understand that. It assumes all communication happen with the system. This is confusing part. Let's simplify it. Okay. Suppose you have two services, service A, service B. If A sends a message directly to B, logical clock can track it. But imagine this instead. Service A update database and database service B reads from database. Okay. Or service A send an email, then WhatsApp or something like that. Service B. Here A still influences B, but not by sending a direct message. Lamport clock cannot see these indirect communication paths. Okay. These hidden direct paths called back channels. Okay. What LC does LC send this mean? LC assumes the local present system. It assumes every piece of information exchange directly between computers inside the distributed system. Expected to travel through external things like databases, human emails, third-party APIs. Okay. And what was this line? I didn't understood. Okay, it answers. The key idea is that Lamport logical clock only tracks message that it can see. Normal communication is like that, service A like this, okay. Indirect communication LC cannot track it. Suppose service A write to database and service B reads the data. Now edit influence B but never sent a message right to B. Lamport logical clock cannot automatically know that B. Another simple example like this. Okay, why this is common today modern. Okay, so one liner Lamport logic clock only follows a direct message between nodes if it follows it. Okay, that means the same thing. Okay, nice. This is obsolete for today integrated loosely coupled systems. And next thing is loosely coupled means like it has microservices and all, right? In 1988, so logical clock was introduced in 1978, and 10 years later, in 1988, the vector clock (VC) 7 was proposed to maintain a vectorized version of LC. Okay, VC maintains a vector at each node, which gives the knowledge this node has about logical clocks of other nodes, while LC finds one consistent snapshot. Okay, that with same LC values at all nodes involved. VC find all possible consistent snapshots, which is useful for debugging application. Okay, let me do with this only. In figure, okay, what I will do this first, and then I will take this part second, right? Learn this in simple language and in brief. So what is the problem with this Lamport clock is it only stores one number at each node, right? Like node A is 5, node B, like, okay. Right, so let's continue. So Lamport clock stores only one number at each node, like each system, right? So node A is 5, 3 like this. It tells the order of events, but it does not tell what each node knows about the others. So we can say like B happened before A and then A happened before C, right? By this logical service. So what is a vector clock? A vector clock stores a list, okay? List means a vector of numbers instead of single number. Suppose there are three nodes called A and B and C. Each node keeps a vector of size 3 like this. So A is 5, B is 2 and C is 1. A knows its own logical clock is 5 and B is 2 and C is 3. So the vector stores A's knowledge about every node. Why it is useful? Because when two nodes exchange messages, they also exchange their vectors. So this each node learn what it has done, what other nodes have done, right? So vector clock captures causality much better than Lamport clock. Lamport clock keep one number per node, okay. Right. Then we have after this part, while logical finds one consistent snapshot with this that with same LC values at all nodes and both. VC finds all possible consistent snapshots which are useful for debugging application. In figure 1, while LC would find AW as the logical clock would find AW as a consistent cut, VC would also find like BW, CW as consistent cuts. Unfortunately, the space requirement of VC is on the order of nodes in the system is prohibitive. So let me do this. Then we will go for physical time, right? So let's capture the figure 1 also as it mentioned about it, right? Where is figure 1, guys? Is it like figure 1? Okay. Function. As you can see here in physical figure, A, B, C are nodes 1, 0, VC, LC 2, 0, 3, 0, 0, 1, 2, 2. WX. So let's keep it like this. Explain this in simple English and in brief, right? So what is a consistent snapshot or consistent cut? A consistent snapshot is a picture of whole distributed system at one moment. Okay, it should not contain impossible situations. For example, impossible is node 0 message sent, not yet, node 1 message received. It's impossible situations, right? So a message cannot be received before it's sent, right? So it is impossible situation here. So this is not a consistent snapshot, right? Okay, so only the possible situations in the snapshot. Okay, look at the figure. Node 0, node 1 it is. Okay, A, B, C, like this. The arrow means B sends a message, X receives the message. So B sends a message and X receives the message. Okay, so 1, 2, 3, 1, 3, okay, whatever. And this, then, so that means B happened before X, right? What snapshot are possible? Snapshot possible one is node 0 A, node 1 W, written as AW. This is consistent because message has not been sent, we are before B. Message has not been sent, we are before B. Okay. Message has not received, we are before X. Everything makes sense. Okay. Snapshot 2 is 01 BW, written as BW. This is also consistent by message has been sent. It will perfectly possible that it is not received X yet. Okay. Snapshot 3 CW, written as CW. This is consistent even though node 0 is moved to C and message may still be traveling. Yeah, this is also possible. Snapshot for AX. A happened, like message is not sent, but X received the message. This is not consistent, right? Because X received a message, but B hasn't seen it yet, so nobody has sent the message. Impossible. Why a logical clock is not enough? Lamport clock only compare one logical clock number. It finds only one consistent snapshot. Example, it will even say other valid snapshots like A, B, W, C, W. Why is vector clock better? Vector clock stores more information in vector instead of one number. Because of this, it can detect all valid consistent snapshots, including AW, BW, CW. Right. It's very useful for debugging because you can examine every possible valid state of the system. What is discharge? We see each node store a vector containing entry of every node. Two vector 1000, 10,000, 10,000, 10,000. So as the number of nodes grows, and memory required grows too. That's why paper says the space requirement of VC is on the order number of nodes, and it is prohibitive in simple words. Vector clocks give more accurate information, but they need much more memory in large storage systems. Alright. So as you can see, one LC logical clock VC. Okay, so this is a 1, 2, 3 like that, right? 1, 3. So this 2, this 3, it is possible, right? In logical clock sense. This is 2 here for B logical clock and 3 for X. So it is possible because B is sending message. 1 and 3 also possible. 3 and 3. Is it possible? I think so. I don't think so. Like that. Okay. Then what can we have is this vector clock 1 0 1 0 2 0 3 0. Okay, like this, and this 0 1 2 2. Okay, whatever it is. Event E happened before event F. If E and F are on the same node and E comes either earlier than F, E is sent event and F is corresponding receiving event, and the value changes based on the previous two. Okay. Now we discuss the physical time value. Okay. The PT leverages on physical clocks at nodes that are synchronized using a network time protocol. Okay. Since perfect clock synchronization is infeasible for a distributed system, there are uncertain intervals associated with physical time. While physical time avoids the disadvantage of LC by using physical time for time stamping, it introduces new disadvantage also. Okay, let me do this part first, then we will do later part of it. Okay. Explain this in a simple English and in a brief order. So let's explain it line by line. Okay. So each physical time. What is physical time? Means using the actual clock on each computer. Okay. Computer A time is this 30 second, 5 millisecond, and this. Okay. Okay, no, 10, 30 minutes, 5 seconds, and this is 6 seconds. Physical time leverages physical clocks synchronized using NTP. NTP is a network time protocol. Is a protocol that makes the clocks on different computers as close as possible to the same time. Okay. For example, internet time server, computer A, computer B. NTP keeps the clocks synchronized. Okay, the perfect clock synchronization is infeasible. This means it is impossible to make all computers so exactly the same time. Why? Because network messages take time to travel. That's correct. Different clocks run slightly faster or slower. That's also correct. Delays are unpredictable. So the different clocks run slightly faster or slower means, guys, the rate of change in their time. Like for some 1 minute is 60 seconds, right? For other 1 minute could be like 59.9999999 seconds, right? Like this. So there will be always be a small difference, right? For example, computer A is this and computer B is like, it's a millisecond difference, right? 7 millisecond difference. So there are uncertainty intervals. right? So there are uncertainty intervals, like since clocks are not perfectly synchronized, every time there is small uncertainty. Example, if a computer A records like this at 10:30 like this, actual time might be somewhere between 0.095 and 0.05 latest possible. This range is called the uncertainty interval. Physical time uses real clock synchronized by NTP, but because perfect every time has small uncertainty interval. Okay. Then what we will have, while physical time about the disadvantage of LC by using physical time for time stamping, that's correct. It introduces new disadvantages when the uncertainty interval are overlapping. Okay, PT cannot order events. So NTP can usually maintain time to within the tens of milliseconds over the public internet and can achieve 1 millisecond in local area under ideal conditions. However, asymmetric routes and network congestion can occasionally cause errors of 100 milliseconds or more. So PT has several kinks such as leap seconds 30, 14 and non-monotonic updates, which may cause the timestamps to go backwards. So let's understand this also guys. Okay. So this paragraph explains problems with using physical time PT. Problem is overlapping uncertainty intervals. Since clocks are not perfectly synchronized, every time stamp has a small error. For example, computer is plus minus 10 millisecond and plus minus is also right. And the actual time could be 9:59:59.995 to this. And same for B, right? These ranges overlap, right? So we cannot be sure which event happened first, right? This is called overlapping uncertainty intervals. Why can this happen? NTP usually synchronize clock well. Public internet about 10-15 millisecond accuracy. Okay. On the local about 1 millisecond accuracy. Okay. But sometimes due to network congestion or different network routes, the clock error can become 100 milliseconds or more. So timestamp become even less reliable. Let me ask this: why clock error can become 100 ms or more, and how simple language and think of NTP like this. Your computer asks a time server what time it is. The server replies, but the reply travels through the network, right? The network is computer A be 20 millisecond and time server and 20 millisecond to this. The round trip time 40 milliseconds here. The NTP can estimate the correct time quite accurately, right? The network congestion large error, like let's say computer A send in 20 milliseconds but receive response in 120. Now the return message delayed because the network is busy. NTP may assume both directions look about the same time, so it calculates the clock incorrectly. The result can be error of 100 milliseconds. Different network routes, sometimes the message goes through different paths like this and receive from different path, right? So why does if the two computer record events 150, but one clock has of 100 milliseconds, then the event B may be actually happened before event A, but the time stamp cannot always be trusted to determine a correct order. Okay, that's understandable. And now okay, yes, right. Okay, problem 2, timestamps can go backwards. Normally the times should always move like this, like from 01 to 02 to 03, right? But sometimes the operating system adjusts the clock. For example, after an NTP correction or because of a leap second, then the clock may look like 10:01, 10:02, 10:01, 800, 10:03. Notice the time went backward in this case, right? This is called the non-monotonic clock, right? Can confuse distributed systems because they expect later events to have later timestamp. One line summary: physical time uses real clocks, but because clocks are not perfectly synchronized and can timestamps are backward due to the clock correction cannot. But I think. But this problem is solved by managing rate of clock and not going backward in time. So is this assumption accurate here? Yes, that's a good observation. Your understanding is correct for many modern systems. The statement of paper is historically accurate, but today it needs some context. Older systems, older auto systems often stepped the clock when NTP found an error. Right? Example like this. This could cause timestamp to go backward. Modern systems today, many systems avoid this by slowing the clock instead of moving the clock backward and change the clock speed. Yeah. Suppose your clock is 100 milliseconds ahead. Instead of doing this, the system does clock runs slightly slower for a while after the 2 seconds or minutes. So, is the paper wrong? Not exactly. The paper says PT has several kinks such as leap second and non-monotonic updates to POSIX time. This is true because some operating systems and NTP controllers still allow time to leap backward. Okay. POSIX time and leap second handling have historically caused these issues. So modern systems like Spanner, Cockroach DB, TIDB avoid relying on raw system time. They use techniques such as clock slowing and monotonic clocks or uncertain intervals, Google to turn. Okay, that's it. So thank you so much guys for being with us, and further we will check the true time and hybrid time. Then we will go the contribution of this work and like that in next series of evaluations. I will end this stream here only, and the stream end here, and